So, let us now talk about matrices, matrix spaces and linear operation. Okay, and again we will recap once again about vector spaces and base span and base. So, linear dependence, linear independence I hope is clear for everyone, right. So, if there are n or p vectors in an n dimensional space, then they are said to be linearly dependent if you can find some scalars alpha that are not all 0, some of them can be 0, but all of them cannot be 0, such that a linear combination of them leads to 0 bar. If that happens, then they are linearly dependent. If not, then they are linearly independent. If there are n linearly independent vectors in an n dimensional space, then they can uniquely represent any vector in that space. Why can they do that? Because if you make a matrix, let us say capital X, which contains x1 bar, x2 bar and so on up to xn bar as column vectors, okay, then X inverse exists. If X inverse exists, then X multiplied by X bar equal to B bar has a unique solution, okay. So, I am now talking about span of vectors in terms of solving linear equations, okay. It is one and the same thing, we have just done it in different ways, that is all, okay. Solving linear equations for this class, I do not want you to think about intersection of two lines, okay, that is really 10th 11th standard material. That way of doing things should not be covered, you know, in a PG level course, okay. We want to think about solving linear equations as whether or not the right hand side can be expressed as a linear combination of the column vectors. If it can be expressed as linear combination of the column vectors, then B bar lies in the space spanned by those column vectors of X bar. If yes, then either unique solution or infinite number of solutions exist. When does a unique solution exist? When those column vectors are linearly independent, okay, which basically also means this, okay. If let us say you have x1 bar, x2 bar are vectors in let us say 3D space, right. So, let us say x1 bar is 1 1 0, x2 bar is 1 minus 1 0. What does that mean? It means that in a 3D space like this, you have your 1 1 bar as this guy, 1 minus 1 bar as this guy, okay. So, this particular horizontal plane that is there, any vector in that horizontal plane can be uniquely represented as linear combination of x1 bar, x2 bar, okay. So, let us say if y bar was say alpha, beta and 0, that can be uniquely represented as a linear combination of x1 bar and x2 bar, which means y bar lies in the span of x1 bar and x2 bar, okay. Let us pose this problem as Ax bar equal to B bar, right, where A is nothing but x1 bar, x2 bar multiplied by some value A1, A2 equal to B bar, which is alpha, beta 0. Question is this possible? So, it is 1, 1, 0, 1, minus 1, 0, alpha, beta, 0. Is it possible? It is possible. Why? Because now we know it lies in the span. But think about the way we have always learnt about solution of linear equations. We will get stuck over here, right. Now we do not know whether you can solve this, not solve this. This linear equation has a unique solution, okay. Why does it have a unique solution? Because y bar lies in the span of x1 bar and x2 bar 1, and x1 bar and x2 bar are linearly independent 2. Because both of these are satisfied, there is a unique solution, okay. And all possible linear combinations of x1 bar and x2 bar are said to be vectors in the column space of A bar or of A, the matrix A. Okay, we will come to that later. Okay. So, revisiting our motivating example to think about A as vector spaces, and if B bar is in span of W1 bar, W2 bar, W3 bar, then a solution exists. Okay. And the span of the vectors W1, W2 and W3 is called the column space. Of matrix A. Okay. So, all possible linear combination of those column vectors of A is called the column space of A. Okay. So, let us take our blending example. Okay. Let us not talk about dynamic model, let us talk about a static model. Okay. When it came to a static model, which basically means if you change F1 by 10%, your height will change by so and so amount. If you change F2 by so and so amount, your height will change by so and so amount, or if you change F out by so and so amount, height will change by so and so amount. Okay. So, our H is some function F1 of F1, F2, F out, and X is some other function F2 of F1, F2, F out. In matrix notations, we will represent this as y bar equal to f bar of u bar, where y bar is nothing but hx, u bar is nothing but f1, f2, f out. Okay. And f bar is nothing but f1 of u bar and f2 of u bar. Again, these are things that you have done, you have talked about nonlinear functions and so on. We are now only talking about them in a vectorial sense. Okay. We say that f bar is a mapping from an R3 space to an R2 space. The input space is called domain space, output space is called codomain space. Most of the times these mappings are nonlinear, but we usually approximate them as linear in the vicinity of the conditions that we are interested in. If the mapping is nonlinear, it is represented at some kind of a function. if the mapping is linear, we can represent it as a matrix multiplication. What is the size of this L matrix? If H and X are output, F1, F2, F out are input, 2 cross 3. Three is the dimension of the domain space, 2 is the dimension of the codomain space, or input space, output space, because L is a mapping from input to the output. Number of rows is going to be equal to number of outputs, number of columns is going to be equal to number of inputs. Okay. Because all the superposition principle and linear addition, subtraction, multiplication on all of those hold, therefore, L is said to be a linear operator. Okay. So, from this point on, as far as control is concerned, I would want you to think of matrices in terms of linear operator that somehow transform an input space into an output space through a matrix multiplication. Yeah, I am just writing something that I just spoke. Okay. So, yeah, we talked about this earlier, that solving Ax equal to B is to find out whether or not B lies in the span of the column vectors of A. Okay. Gilbert-Strang, so what book do you would want to refer to? It is Linear Algebra by Gilbert-Strang. The book is available, I think, for 500 or 550 rupees in any of the bookstores. So, if you are interested in linear systems or control systems, definitely a book to buy. Okay. He also has lectures in MIT OpenCourseware. He also has lectures where he combines linear algebra fundas with data analysis. So, those are also very interesting new lectures that he has recently put up. Okay. Gilbert-Strang, I mean, if you have done a linear algebra course, you would have heard about the 4 fundamental subspaces. The 4 subspaces are column space, null space, row space and left null space. We are only going to talk about column space and null space. Why? Because row space and left null space are nothing but column space and null space of A transpose. If you have not understood this, perfectly fine. This statement was only meant for people who have done linear algebra course using Strang's book. Okay, so although Strang talks about 4 subspaces, I am only going to talk about 2 subspaces, and those 2 subspaces are null space and image space. Okay, image space is nothing but column space. Okay. Oops. Okay. This is just the definition, do not have to write it. Tomorrow's class I will start from this point. Okay, this is where we will start tomorrow's class in definition of null space and image space. Because you guys have not done SVD before, we will talk about SVD also in tomorrow's class. Okay, I was kind of planning to very briefly touch upon it and mostly skip it, but because most of you have not done SVD, we will go over that also a little bit slowly.